Okay, I am recording. All right, we've got a bunch of main ideas for thermal energy and heat flow. When two objects are in thermal contact, and that means that somehow they're connected in some way, and we'll talk about ways that heat flow can occur probably tomorrow, I think, or Wednesday, I mean. But when two things are at different temperatures and it's possible for heat to flow from one to another, the temperature of the system will change. Now, there's a note in your book. Heat is not the temperature of something. If you think of heat, it could be a verb, and maybe if you keep that verb idea of heat in mind, it's not always necessarily that we'll be using it as a verb, but it may help you to keep these ideas straight. Heat flow is energy that is flowing from one place to another as a result of a temperature difference. And when there is a heat flow into or out of a thermal system could be something as simple as a cup of water, or maybe the cup itself. All sorts of different things can be thermal systems. But when there is heat flow, that's energy going into or out of it because of a temperature difference, the temperature of the system can change. And so you need to shut the door so if the dog starts barking, it's not so annoying. The heat capacity of a thermal system, it's a measure of the heat required for an incremental temperature change. And incremental, we're talking about a really small one. And we'll use dq for heat flow in here. I don't know if that's the same letter you would use in a chemistry class or not, but we're in physics, we tend to use dq for that. And then dt would be the temperature change, and dq would equal a capital C times dt, where C is the heat capacity of the system that we're talking about. And again, the system could be something as big as a house, or as big as a skyscraper, or all sorts of different things. But it'll be somehow the heat capacity of that system. And it could be something like a 6-pack of pop. That could be thought of as a system. Now, the specific heat of a substance is the heat capacity for some particular amount of that material. And usually it'll be something that is a fairly specific definition, I guess, for specific heat. Anyway, in chemistry, you might have used molar heat capacity. That's the heat capacity per mole. And specific heat that we're going to use is the heat capacity per gram. Sometimes in chemistry, you might use grams. Sometimes we'll be using kilograms for that. It depends on how the problem is stated. And so specific heat is the heat capacity per unit mass, actually, is what it happens to be. And for some things, that heat capacity may depend on how the temperature changes. And this will be more important for gases. With gases, if you have a constant volume heating going on, the gas would be confined to a particular volume, and so it'll have one heat capacity for that, whereas maybe you would have a constant pressure situation going on instead. You might have a different heat capacity for that. So we'll worry about that if and when we get there. When a material changes phase, that means by phase, we mean going from, say, a solid phase to a liquid phase. That would be like going from water ice to liquid water. That would be a phase change. Or if it goes from liquid water to water vapor, that would be another phase change. And you have to have heat going in that direction at least. And the temperature would not change during that phase change. So when you melt an ice cube, you go from a solid form to a liquid form, and you'll go from a solid form at, say, 0 degrees Celsius, depending on the pressure, but you'd go to liquid water at also at 0 degrees Celsius. So water is a kind of a unique thing, but that happens with any material that you happen to melt, is that you go from a solid form at the melting temperature usually, and the other one. And then this is a table out of your book that is going to be absolutely impossible to read, I think, but it's got the approximate specific heats and molar heat capacities at constant pressure for a bunch of different things. And they're not going to be readable, but this is a table that's in chapter 17. And then it's also got the heats. There's another table that has heats of fusion and vaporization. And the heat of fusion is how much heat, the specific heat for going from a solid to a liquid. Its units are joules per kilogram. We'll be using joules for the most part for our energy units on these things. And then it's also got the heat of vaporization, which is also in joules per kilogram. And it's got the normal boiling point and melting point for a bunch of different things. So there's that going on. Let's see. Helium remains a gas all the way down to 4.216 Kelvin, and which is minus 268.93 degrees Celsius. And then it becomes a liquid, and it never does become a solid. So kind of a unique thing in that way. Okay, just to talk a little bit about units. A lot of times units of you may run across calories, and I don't think we're going to use calories much in here, but they do show up someplace. And as far as converting from calories to joules, 1 calorie is equal to 4.186 joules. And you've probably heard this before. This is not a food calorie. 1 food calorie, and the abbreviation for a food calorie is often a capital C. It's actually equal to 1 kilocalorie. That's calorie with a lowercase c. And it's equal to 4,186 joules. So a food calorie is equal to a fair amount of energy there. At least as far as joules are concerned. That would be like, I think I maybe demonstrated this in class. If you drop a 100-gram mass onto your foot and you've dropped it 1 meter, it'll have 1 joule of energy when it hits your foot. Well, 4,186 joules means you drop 4,186 times 100 grams. It actually ends up being about 418.6 let's see, kilograms is what you'd have to drop. And if you drop that 1 meter, then you'd have a kilocalories worth of energy, but you'd smash your toe if you dropped. That's 900 pounds worth of weight that you just dropped onto your foot. So you wouldn't want to do that anyway. But things that we're going to be using here, for the most part, if we talked about the heat required for some particular temperature increase, it might be capital C delta T. And this capital C isn't standing for a food calorie. It's standing for the heat capacity of some system that you're heating up. But what we'll use more often, we'll be using specific heat. And if we want to know the amount of energy required to raise the temperature of some mass by some temperature difference, we'll use a lowercase c and a delta T. And this little MC would equal that capital C. But this would be would be talking about the mass of, say, a chunk of copper, and then we'd have to use the specific heat of copper, which is the heat required per unit mass to raise the temperature by 1 degree Celsius or Kelvin, or 1 Kelvin. Let's see, were there any other units that I had in mind? The calorie with a lowercase c, this is kind of historical, but it's the amount of heat required to raise the temperature of 1 gram of water by 1 degree Celsius, and I forgot where the temperature difference is. It might be on that other sheet. Nope, it's not. Anyway, it's from like 14.5 to 15.5 degrees Celsius is where that shows up. Other units of heat, there's something called a British thermal unit, which is the heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. And I can't remember exactly where that, it's like 55 to 60 or 56 degrees or some weird thing like that. We are not going to use British thermal units in here, so don't worry about that when we're talking about heat. But anyways, we'll have lots of different things going on here. And just an example of how we might do something. How much energy is required to raise the temperature of 335 grams of water from 15.0 degrees Celsius to 93.3 degrees Celsius, which is considered the ideal temperature for brewing coffee. So this would be about a cup's worth of coffee. Actually, it's about close to 12 ounces, I think. But anyway, it might be the size of a coffee mug, which vary all over the place. Anyway, 15 degrees Celsius might be the temperature of your tap water, and that'd be the heating it up there. So how much do we need? Well, this is just going to be a Q equals MC delta T problem. And we're given the mass, it's 335 grams. For water, if I look up its specific heat, and I'd have to go to this thing because as a liquid, its specific heat is actually 4,190 joules per kilogram Kelvin. So joules per kilogram Kelvin, and that capital K stands for Kelvin. Okay, well, if we're talking about temperature differences, we've got a delta T here. It's the same in degrees Celsius as it is in kelvins. So I can deal with that. Now, this is per kilogram, so I need to convert that into kilograms. And you can do that in your head pretty darn fast. In fact, you just move the decimal spot over 3 places and you get 0.335 kilograms. But if you don't have that memorized, just go 335 grams times 1 kilogram per 1,000 grams. This is a 1 because 1,000 is equal to a kilo, and you get 0.335. So the amount of heat required here, we can now figure this out, is going to be 0.335 kilograms times 4,190 joules per kilogram Kelvin times, okay, it'll be 93.3 minus 15.0, and that'll be degrees Celsius, but it's the same as a Kelvin when it's a temperature difference. And so I'll just take those 93.3 minus 15.0, and that'll be the number of Kelvin that I have, kelvins. For a long time, I thought Kelvin was a plural of itself, but I guess you can stick an S on the end of it. So kelvins seems a little weird. Like 3.3 minus 15.0. Okay, and I get, seemed like a huge amount of heat, but it's because water actually has a large specific heat. There aren't many things that have specific heats as high as water. In fact, let's see. Yeah, on the table in the book, it's higher than anything else. In fact, it's almost twice as high as the next highest thing, or the next a couple of them. Ethylene glycol, which is used in antifreeze, and ethanol have, well, ethanol is 2,400 joules per kilogram, and water is 4,190. So it's a lot more anyway. But I get about, I only have, do I have 3 sig figs? I do. So it would be 1.10 times 10 to the 5th joules. So fair amount of heat for just for making a cup of tea or a cup of coffee. So our first kind of calorimetry problem. Let's see, is this jumping too far ahead? Maybe not. I've got a problem here that's kind of weird. Oh, that one's probably split up on 2 pages. Yeah, let's go ahead and try one of these. It's more complicated. We have a 3.00 times 10 squared cubic centimeter glass. Okay, it's filled with, that looks like 100 grams of ice to 3 sig figs at 0 degrees Celsius and 200 grams of water at 25 degrees Celsius. What will be the content of the glass, or characterize the content of the glass after equilibrium is reached and neglect transfer to and from the environment? So any heat flow that's going on in here is going on between the glass, the ice, and the water. And I think I'll probably need to look up the specific heat of glass in here, and I don't have it. Um, I think I'll replace glass with styrofoam cup because I don't have a specific heat for glass on my thing here. And the styrofoam cup, we're just going to ignore whatever heat or heat it might give to the water or heat it might absorb from the water. So we'll just consider the ice and the water. Okay, so the water is warmer, the ice is colder. Something I can think of this as an insulated system or a system that's isolated from its environment, and they say to figure that. So something I can say is that the heat into the ice plus the heat taken from the water is going to equal 0. They'll be of opposite signs. This will be a positive thing. This will be a negative thing. And so combined, it's going to equal 0. So let's try and figure out what's going on. Heat into the ice, it's at 0 degrees Celsius. So any heat that goes into there is going to melt some or all of the ice. Okay, heat taken from the water is going to cool it down from 25 degrees Celsius to some lower temperature. Now, here's the thing. I don't know ahead of time if that water will be able to melt all of that ice. So I'm going to do a little side calculation and figure that out. I'm going to see heat taken from water. Now I'll try to remember to write big so you can see it. To drop temp to 0 degrees Celsius, okay, or 0.00 degrees Celsius. It's at 25.0 degrees Celsius. Well, I would take the heat that would go from it would equal the mass of the, I'm going to use water, M sub W for water, times the specific heat of the water times the temperature. Final temperature is going to be 0.00 degrees Celsius, and the initial temperature is 25.0 degrees Celsius. And the reason I'm doing this is I'll figure out how much heat would take to drop its temperature to 0, and then figure out how much heat it would take to melt the ice. And it'll tell me whether or not all of the ice will melt or not. And so we'll just find that out. Okay, well, how much water do we have? We've got 2.00 times 10 squared grams of water. So I'll just leave it as grams. Well, 2.00 times 10 squared grams times 1 kilogram over 1,000 grams. And I think I'll end up with 0.200 kilograms when I do that, but you can check it if you want. 200 over 1,000 is 0.200. We could have done that in our head. Now, the specific heat of water, that's 4,190 joules per kilogram per Kelvin or per degree Celsius, because we're always multiplying this times a temperature difference. And my temperature difference is minus 25.0 degrees Celsius. You can get away with that when you're talking about a temperature difference. And for this calorimetry unit, we're almost always talking about a temperature difference. So we'll see what that is. Anyway, that heat that the water has available to give up when it's dropping from 25 down to 0 degrees Celsius, forgot his degree symbol on that one, is going to be, let's see, until this morning, I'd forgotten that water's specific heat was 4,190 joules per kilogram degree Celsius, but that's one that gets stuck in your head after a while because often the problems deal with that. And I'll be able to keep 3 significant figures on this. It's minus 2. Let's see. It's either 0, 9 or 1, 0. I'll give it a 1, 0 times 10 to the 4th joules. And I know that's a small exponent, but that's how much. Now, the heat to melt the ice, okay, let's see. I'll call this Q sub W. Heat to melt the ice. This is the way it works when you're having a phase change. It's just going to be the mass of the ice times the heat of fusion for water, and I forgot these. Oh, it's L sub F is the symbol for the heat of fusion for ice or water. And how much ice do we have? We've got 100 grams, which is 0.100 kilograms. Check that. Once you've done them about a zillion times, they kind of stick in your head. for the unit conversions. Now, the heat of fusion of ice is the water, 334 times 10 to the third. And this is just joules per kilogram because there's no temperature change that takes place when it changes state here. And let's see, this would be 3.34 times 10 to the fourth joules. Okay, now the water has only 2.10 times 10 to the fourth joules available when its temperature is dropping from 25 down to 0. That's not enough to melt all of the ice. However, it's enough to melt some of the ice. And so we can figure out with this much energy available how much of the ice we're going to melt. I can now characterize the content of the glass after equilibrium is reached. There's going to be, as a verbal description, there is going to be water that's at 0 degrees Celsius. There's going to be some ice that's still at 0 degrees Celsius, but there's also going to be some ice that's melted. And we have enough information to figure that out. If we're melting ice, how much ice can we melt with 2.10 times 10 to the fourth joules? Well, how much ice is melted? Is melted with 2.10 times 10 to the fourth joules. Now, I'm having to do this kind of stepwise because there really isn't a simple way to characterize it otherwise. So, well, I know the Q, I know the L F sub I don't know the mass, but I can solve for that in this expression here. M sub I will equal 2.10 times 10 to the fourth joules divided by the heat of fusion of water right there, 334. Oh, this is LF sub I on the bottom. 334 times 10 to the third joules per kilogram. And just unit-wise, a joule divided by a joule per kilogram will end up being, you flip it and multiply, a kilogram. The joules will go away. And this is actually Q divided by M sub I. And so this will tell me how much of the ice melts. So and I get 0.06. I guess I've got 3 sig figs still. 629. It'd be 6.29 times 10 to the minus 2 kilograms, but I can write that as 0.0629 kilograms, which is 60, pretty close to 63 grams of the ice. So of the 100 grams of ice that we had, 63 grams or 62.9 grams are going to melt. So then that 60, that means we're going to have 260 or 2.63 or 0.263 kilograms of water in there, and then the remainder of the 100 grams of ice, which is going to be about 37.1 or let's see, 0.0371 kilograms, of ice is still frozen. So we've got a mixture of ice and water. And that's how much melts. Oh, and then it says repeat your calculations for 0.500 kilograms of ice and 0.250 kilograms of water. Okay, so we're changing things around a little bit here. Originally we had all right, they changed units on us too. This is 0.100 kilograms. This is 0.500 kilograms. So we've got 5 times as much ice. However, we've changed the amount of water that we have from 200 grams to 0.25, or yeah, 200 grams to 250 grams. It's just a repetition of the same calculation. So I guess we could go ahead and do it again. It's not going to tell us to do so. So now we've got 0.500 kilograms of ice and 0.250 kilograms of H2O at 25.0 degrees Celsius. And I'm pretty sure, whoops, that came off the page. Anyway, I'm pretty sure we still, even with 0.250 kilograms of water, we're not going to have enough energy to melt 5 times as much ice, because actually the energy to require to all of that ice would actually be 5 times as much as this. And we're not going to have that much energy available. We're only going to have, I think, 20% more than that. So let's look at this. Energy, whoops. Avail, I can't spell. This is going to be the energy available in the water, and this is dropping it down to 0 degrees Celsius. So the Q that the water, for the water, the heat flow out of the water, is going to equal its mass, which is 0.250 kilograms. And let's see, C for water, 4,190 joules per kilogram degree Celsius, or kilogram Kelvin. It's always temperature differences when you're using this. And let's see, oh, delta T, which is 0.0 degrees Celsius minus 25. Rats keep running out of room on here. Going on to the other piece of paper. Okay, well, that heat available, and I'll call it Q sub W again. It's going to be negative because I've got a negative temperature difference. So it's amazing how far I can get before I actually turn my calculator on. I'm not even looking at the screen of it. Yay. And for some reason, I put in 0.25 degrees instead of 25 degrees. So I was only off by a factor of 100, but I get minus 2.62 times 10 to the 4th joules that the water will give up, which is, looks to me like that's 20% greater than what we had the first time. So no surprise there. Okay, how much ice can I melt with that much energy that's been given to the ice? Well, For melting ice, I'll be thinking about the heat flow into the ice is going to equal some mass of ice times the heat of fusion for the ice. And the mass that I can melt with that much energy. Now, this is it's a negative energy amount for the water, but it'll be a positive energy amount for the ice because that energy is going into the ice. So I'll just change the sign on that, and it'll be Q sub I over LF sub I. And actually, probably 20% more than the last value, but it'll be positive here. 62 times 10 to the fourth joules. And on the bottom, let's see, that was 334 times 10 to the third. 10 to the third joules per kilogram. I'm not sure why with these heats of fusion and vaporization, they're written with, usually we'd think of this as 3.34 times 10 to the fifth joules per kilogram. But in the case of the specific, or the heats of fusion and vaporization, they're all written with a 10 to the third exponent. Maybe that's just the most convenient thing. I'm not sure. But when you have exponents that are always multiples of 3, that's called engineering notation. And it's one of the things on your calculator. Well, I guess we do that when we're dealing with wavelengths of visible light. We measure them in nanometers, which is an exponent that's divisible by 3 as well. So just something that's done. Okay, and this time I get 7.84 times 10 to the minus 2 kilograms, which would be, I guess I could think of it as 78.4 times 10 to the minus third kilograms, or you could think of it as 78.4 grams, or 0.0784 kilograms. So in that second instant, we melt 0.0784 kilograms of ice. And we'll be adding that to 0.250 kilograms of water. The temperature of the water is going to drop all the way down to 0 degrees, so you'll have a nice cold drink when you do this, if that's what you happen to be doing. And let's see, we'll still have 0.500 kilograms minus 0.0784 kilograms, which is about 0.422 of ice. So, because we started off with 500 kilograms of ice there, or 0.500 kilograms of ice. So that's what we'll have. We'll have that much ice sitting in 0.250 plus 0.0784, which is, I think, is like 0.328, if I did that in my head right, kilograms of water. So you can do all kinds of stuff with these. Okay, a couple of other problems. Here's an interesting one, another phase change one. We have steam at 100 degrees Celsius is added to ice at 0 degrees Celsius. Find the amount of ice melted and the final temperature when the mass of steam is 0.0100 kilograms and the mass of ice is 0.0500 kilograms. Well, this will be interesting. Let's figure out first how much energy to melt that many kilograms of ice. And melt 0.0500 kilograms of ice. I don't know what the final state of this thing is going to be yet, and I need to have some ideas of what some of these energy amounts are. So to melt that much ice, it would be the Q needed would be mL heat of fusion of ice. And sometimes you just see L sub F for this. It doesn't really matter. But I know I've got 0.0500 kilograms. Times that 334 times 10 to the third joules per kilogram. And so the heat to melt that much ice isn't any big deal, but 1.67 times 10 to the fourth joules. Okay, so that's part one. Now I know how much energy it would take to melt the ice. Do I have that much energy in, I might. Let's see. Mass of steam. Energy given off by steam. Sorry, I probably can't, you probably can't read that. 100 degrees Celsius. When they say 100 degrees Celsius, I'm pretty sure we've got some sig figs on there, like 100.00 degrees Celsius. But anyway, I would have the energy given off would equal, and here this is going to be, well, actually that'll be energy added to this, but in this case, it's going to be given off by the steam, but it'll be available to be given to the ice. So let's just see how it works out. It'll equal the mass of the steam times the heat of vaporization for water. And I'm just going to leave that alone. I've got 0.0100 kilograms. And I'll be multiplying by the heat of vaporization for water, which I need to track down here. And there's no possibility of you guys being able to read this, but I go over here and it's at actually at 0.00 degrees, no, 100.00 degrees Celsius. 2256 times 10 to the third. So joules per kilogram. Okay, this is a big number. It takes a lot of energy to vaporize water, and we'll find out if it's enough. Have 2.256 times 10, actually 2.26 times 10 to the fourth joules is how much that steam would lose in energy condensing from steam to water. Well, this number is bigger than that one. So just when that steam is condensing to water, it's going to have more than enough energy to do that, which means if we condense that much steam, we're now going to have this steam is going to become 0.0100 kilograms of water at 100 degrees Celsius. And the ice is going to be, well, we had 0.0500 kilograms of ice, but it's going to be completely melted at 0 degrees or that much water, 0.0500 kilograms at 0 degrees Celsius. So that's a new situation. We're going to imagine, okay, let's add 0.0100 kilograms of water at 100 degrees Celsius to 0.0500 kilograms of water at 0 degrees Celsius. And that's part two of the problem, because I know I'm going to melt all the ice. So I can ignore these calculations I used them, but now I can say we have 0.0100 kilograms of H2O added to 0.0500 kilograms of H2O at, I forgot to put the state here, at 100.00 degrees Celsius, and added to this at 0.00 degrees Celsius. And I could express all these temperatures in Kelvin if you were happy with those, but we don't need to. You can just go with this. Well, here's what we're going to have. We'll have a bunch of heat that's going into that cold water. So I'll have the mass of what was formerly ice times the specific heat of water times some T final minus 0.00 degrees Celsius. That's going to be the heat that goes into the ice, and I'll have the mass of what used to be steam, the 0.0100 kilograms, times the specific heat of water, which is, because that's what it is now, times, here we'll have a T final minus 100.0 degrees Celsius. And this is going to be positive, this is going to be negative, but we have this system isolated from everything else, or we're not given any way to deal with it. So that'll end up being 0. And we've actually got the specific heat of water in both terms, so I can divide that out. And I'll just say Mi T final plus mass of the steam T final. I divided the C's out. Mi times 0 degrees Celsius is 0. So that's just going to drop off the map for us. But then I'll have minus Ms at 100.0 degrees Celsius is going to equal 0. And I think I can let's slide this up here. I can kick that term across and say, yeah, I'll do that. Mi, and I'm going to factor, actually, I'll factor the T final out of there. And I'll get T final is going to equal the mass of the steam over the mass of the ice plus the mass of the steam times 100.00 degrees Celsius. And I'll be down to 3 significant figures when I'm done, but the mass of the steam was 0.0100. Whoops, kilograms. Mass of the ice plus the mass of the steam is 0.0600 kilograms. And I multiply that by 100.00 degrees Celsius. This looks like 1/6. This looks like about 16.7. Yeah. Yep, 16.7 degrees Celsius. So that's about tap water temperature is what we're going to end up with here. But that was a fairly complicated calorimetry problem, is trying to deal with that. I think I've got one on here. Yeah, this will work. This might be a fun problem to do. 0.951 kilogram block of copper at 20.2 degrees Celsius. Now, that's not all that warm. That's roughly room temperature, actually, but it's dropped into a large vessel of liquid nitrogen at 77.34 Kelvin, and that is the boiling point of nitrogen. How many kilograms of nitrogen boil away by the time the copper reaches 77.34 Kelvin? Okay, well, they tell us more or less that the copper is going to drop down to 77.34 Kelvin. And we're given the specific heat of copper. We're given the heat of vaporization of nitrogen. And so should be able to figure this out. Let's see if we can write a single equation here. Most of the nitrogen is probably, well, we're not even, it says a large vessel of liquid nitrogen. So some of it's going to stay as liquid nitrogen, and some of it will be boiled away. So we can say heat vaporizing some nitrogen plus the heat lost by copper is going to be 0. Okay, we'll think of the rest of the nitrogen stays a liquid at 77.34 Kelvin, and the heat, the copper is going to drop down to that 77.34 Kelvin, and won't, once they're at the same temperature, there's no net heat flow between the two. So the system would then be in equilibrium, is what we'd call it. All right, well, the heat vaporizing the nitrogen, I'd have some mass of nitrogen times the heat of vaporization for nitrogen. And that'll be positive. Let's see, it becomes vapor at the same temperature as the liquid nitrogen, but that vapor is not going to be in contact with the copper anymore, so it's not really going to get heated up, or it'll just stay sitting above the vessel or something like that. But and then I'd have the mass of the copper, mass of Cu. That may be impossible to read, but I'll have the let's see, the specific heat of copper, C sub Cu, times delta T for the copper, which it's going to be negative. It'll be 77.34 Kelvin. This is going to equal, in Kelvin, it'll be 273.15 Kelvin plus 20.2 Kelvin, which is about 293.35 Kelvin, actually 293.4, but everywhere else we've only got 3 sig figs. So no, we've got 4 on that temperature. We've only got 3 on that one though. Oh well, we'll lose a sig fig on this. Okay, and this will be negative. This number's smaller than that number, so we're going to have heat loss here, heat gain here, and that will equal 0. So the mass of the nitrogen will equal, I do bring this to the other side, and that changes its sign, but I can just swap the order of the subtraction there. I'll have mass of the copper, specific heat of the copper, and then I'm going to go ahead and do that subtraction. Order 0.4. That is 216.1. Yeah, I still have 4 sig figs on that. Kelvin, temperature change, and I divide by the LV, it's F, which they give me. I think they give me everything. Yeah, they give me the specific heat of copper, which only has 2 sig figs, so we'll be down to that. Just plug in numbers. The mass of the copper, 0.951 kilograms. The specific heat of copper, I wonder if I can get if the table in here has a better value than that. Iron, lead, mercury, copper. Nope, it's just that. So that'll be our weak length. Joules per kilogram Kelvin. And then 216.1 Kelvin, but we'll be down to 2 sig figs when they're done. And then the heat of vaporization of copper is 201 times 10 to the third joules per kilogram. So, all right, and we'll stop with this problem, but 0.951 times 390 times 216, and hopefully I put all these in right. That would kind of like 1 by 10 to the third. I get about, let's see, 0.40 kilograms of the nitrogen would boil off. Well, yeah, it'd boil off. It'd be vaporizing in that case. So that was another one. And so various problems like this. I'll put up some suggested ones to work on for this topic because these are, I don't know, they aren't hard once you've done a bunch of them, but until you have set up a few, check out these examples again, look at the examples in the book, but they can be a bit bewildering until you've done a few of them. So I'll stop there and